So in this video, I just wanted to recap again the fundamental theorem of calculus. Now this is what we're going to be looking at is called the first fundamental theorem of calculus. And it's very important. It's what first-year calculus students learn. And it relates geometric aspects, geometry, to integral calculus. And integral calculus is really the inverse of differential calculus, as we've seen. It's taking the integration is taking the antiderivative per se to a function. And so when you take the integration of a function, you go up in order in magnitude, but the resulting function that you get out of taking the antiderivative of a function is in itself the derivative of even a higher order function. So you can think of these things as equivalent in the sense that we're really talking about the same thing when we talk about integrating. It's just the direction that we're moving in. Differentiation, we're moving down when we take derivatives in order of, let's say in a hierarchy sense, the power or the order of the function is reducing in order. For example, x to the fourth, the differential is 4x to the third. So when you integrate, you're going up in power. So you, let's say, integrate x to the fourth. The function that it derived from was 1/5 x to the fifth. And so when you take the integral of x to the fourth, you end up with a function 1/5 x to the fifth. But that function in itself is equal to the derivative of a higher order function of x to the sixth. So you can see how that these things are connected. These derivatives and integrals are connected. It tells you which way really basically you're going. But then when you look at definite integration, you're looking at areas under the curve between two limits or 2 points of integration on the x-axis. So you're looking at the area under the curve, under the function, between x1 and x2 on the x-axis. And Riemann then, he looked at the same problem from a geometric point of view and realized that if you squeeze the rectangles down, and we'll demonstrate this graphically, he worked out that the sum between two given points of rectangles, as they divide up the area under the curve between those 2 points on the x-axis, become the area exactly when you squeeze the delta x of the rectangles to 0, which is by taking the limit of the number of rectangles that you fit in the curve to infinity. And making this realization, he showed or demonstrated that the integral, definite integral, is the same as this Riemann sum. And so we'll go through that derivation, and we show that equivalency. Now I don't go through the proof of it, but I get to the point where he made that statement where the integration, the definite integral, is equal to the sum of geometric figures, basically rectangles under the curve. So that is what they call the first fundamental theorem of calculus. And it was the first time that anybody had taken calculus and put it on a foundation, on a theoretical foundation that was sound, solid, accepted by mathematicians. For some 200 years, almost 100 some plus years, 150 plus years since the time of Newton and Gottfried Leibniz. The calculus was not on a firm theoretical foundation until Riemann and his limits, his Riemann sum, and then taking the limit to the number of rectangles being infinite between two points of interest on the x-axis. So, with that, we go through this derivation, and then we make a couple of examples of integrating and obtaining sums using sums of areas using the definite integral. So I just thought that this video was a little bit clearer on the basic concept of the fundamental theorem of calculus and how powerful it is, because not only do you get areas, you get volumes, you get centers of gravity, centers of mass, all kinds of physical phenomena, torques, and all kinds of physical phenomena can be described using calculus, and that's why it's such a powerful mathematics that's so crucial, essential to our understanding of science today. So with this, this is enough of an intro. Let's get down to the derivation. I think it's a little more intuitive in this video than in my previous video, where I kind of introduced some of the concepts of the fundamental theorem of calculus, but I don't think I made the tie-in very explicit, where the Riemann sum, which represents the geometric side of things, to the definite integral. So without further ado, here we go with the fundamental theorem of calculus and a couple of examples. And we're looking at the fundamental theorem of calculus, and we're looking at integration. And so if we have two axes, x and y, and forgive my disdainful art, and we have a function f of x, and we have an area here that we want to find the area of under this curve between x final and x naught. We want to find the area under the curve between the x-axis and the y-axis, under the curve, and bounded by x naught and x naught. So, if we take a look at rectangles. Now, we divide this area up so many times. Let's say we, oops, I made a mistake. All right. We take this and we bring it up, and we bring it up. I've halved these. Okay, so let's just keep it simple at this point. And we've got 1, 2, 3, 4 divisions. 4 divisions. So delta x, whoops, I wrote this wrong. Delta x is equal to xf minus x naught. Whoops, boy, I'm talking and not thinking. X naught divided by the number of divisions that we have between xf and x naught. In this case, we have 1, 2, 3, 4 divisions. And our delta x is right there. All those are delta x. So basically we look at our different again, I wish I had a little better hand control, but these are different areas are different rectangles, and this is our y-average right here, right there, right there, right there, and right there. And we have our rectangles like this, and right here, and right there, 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 and right there. So the area of our rectangles, let's say whatever ith rectangle there is equal to delta xi times y average I. Well, if we look at x and make a table, x1, and let's take a look at this here a little more closely. We're going to have x1, x2, x3, x4, and x5. So x1 is our starting point, that's x naught, and x5 is our final, that's xf, and we have x2, x3, x4, x5, and that is equal to x1 plus delta x equals x2 plus delta x equals x3 plus delta x equals x4 plus delta x, but these are all equal to this is equal to x1 plus 2 delta x equals x1 plus 3 delta x equals x1 plus 4 delta x. So xn equals x1 plus n delta x. But remember, delta x was equal to x1 plus n delta x, which was xf, whoops, well, we'll just leave it like that for now. And let's see how I had this all worked out. Now we'll just leave it like this. And we won't even worry about this one at this point. But that would be true if we had the... So, now let's see, now the area, remember, area of a rectangle is simple. It's length times width. So area equals LW, L times W. And in this case, it's YI average, AI equals YI average times delta X. And we get the total area between x final and x1. We say that area is approximately between I equals 1 and n. But y average, remember, we gotta say that y average I equals f of xi. All right, so we have yi average times delta x, and that's equal to I equals 1 to n of f of x naught plus I delta x times delta x. So we have delta x, which is x to the f minus x naught on n. Now this becomes exactly the area, not approximately, but exactly the area, when we take the limit of as n goes to infinity, as n goes to infinity, delta x goes to 0. That we can't forget. So we've got I equals 1 to n y average, which is f of x naught plus I delta x times, I better erase this part here because this, my hand's getting in the way, times x f minus x naught on n. That is equal to, and we're going to get rid of this table here. All right. We're just take a moment, get rid of this extraneous stuff. Okay, that happens to be of calculus, and Riemann made this equation basically during the 1860s, Bernhard Riemann, and this is basically called the Riemann Sum right here, and it shows the equivalency to this integral. So that is the basis for integration when we take a look at this. And basically what that's saying is when we look at these individual rectangles and we squeeze them so that they're tiny and the delta x goes to 0, the area is no longer approximate, but the area becomes exact. So that's basically what this sum says. And so this is the fundamental theorem of calculus in a nutshell. This is basically how it's equated, how it's thought to be. And this was the first time mathematicians had been able to put the calculus into with some sort of a theoretical foundation. Before that, calculus, up until the 1860s, there was no theoretical basis for calculus that had been proven. But Riemann, actually, with his Riemann Sum, was able to take a look at calculus and put it on a firm foundation. So this allows us to take a look at any function. Let's, oops, I always forget to do that. All right. So if we had any function, let's say Are you going somewhere?
Yeah, going to the vet.
Oh, okay. You won't be long, I guess.
No.
All right. So let's say we have this function y equals well, let's 3x to the third plus 2x squared minus 1, and we want, let's say, the area between, let's I don't know what this thing is going to look like, but let's say it kind of looks like this. All right, just, well, maybe not so awful. Let's take a look at this and make it smoother. Let's make it like that, and let's say it goes off like that somewhere. And this is our x-axis, and this is our y-axis, and we want the area. The problem is the area under the curve, and this is our curve, between x equals 1 and x equals 3. So basically our area then becomes x naught to xf f of x dx. And we can say this is 1, and we can say this is 3. So we want to find the area under this curve between those two limits on the x-axis. So we just take the integral, and we've got 3/4 x to the fourth plus 2/3 x to the third. Remember our rule that we established in our last video for integrals, minus x. And since we have a definite integral means that we have limits 3 and 1. We don't have because we have defined the limits of this integral. So now what we do is we say that the area now is 3/4 times 3 to the fourth plus 2/3 times 3 to the third and minus 3. And we bracket that. And now we do the other limit, which is 1. We first do this, and then we subtract this from that. We basically f of x final minus f of x initial. That's basically what, or g. That's really, we should say g. So this we're going to call these g because we used f. F was our integrand. The integrand, I'll show you what the integrand is in 1 second. This is our integrand here. We called f of x the integrand. So when we integrate, we come up with a new function, g of x. And when we evaluate g of x, we have to take the final value minus the initial value, and that's why Okay, so when we do this calculation, we have, and we'll work over here, area equals, and this is an exact area, not an approximation, 3/4 times 81. That's what 3 squared is 9. 9 times 9 is 81. So 3/4 of 81 plus 2/3 of 27 minus 3 minus 3/4 minus 2/3 plus 1. And when we do the estimate, just a second, let me do the calculating here. Just take a second with my calculator. And we have 81 divided by 4 times 3, and that's 60.75. 60.75 plus, and this is 2/3, so 27 divided by 3 times 2 is 18, plus 18 minus 3 minus 0.75 minus 2/3, 0.667. 667 plus 1. And that turns out to be, and let's clear this and add it, 60.75 plus 18 minus 3 minus 0.75 minus 0.66667 plus 1. And the area is 75. Oops. Let's see if I got a pen. Yep. 75. Why isn't that writing? 75.333. And that's the answer. That's the area under the curve for this particular curve. And we can do that for any function. Now, what I like is another approach. And let's close that and get a new board. Okay, so now let's look at it this way. What was our function? We said it was, let's go back and take a look at that. It was 3x to the third plus 2x squared minus 1. Let's go close that. And back here. Our f of x we have f of x equals 3x to the third plus 2x squared minus 1. Okay, and we had between x is 1 and x is 3. Well, we can think of this, and I mentioned this in the last video that there are infinitesimal areas that we're adding up from the x-axis up to the y-axis, or the function f of x, which is our limit of integration. So what we do is we go dy dx, and our area, our differential area, is equal to dy dx. And we're adding these up. There are going to be an infinite number of these. We're going to be adding them up between the x-axis and the curve itself, and between 1 and 3 on the x-axis. So we say that dA is equal to our limit on the x range is 1 to 3, and in the y range it is 0, x equals 0, or y equals 0, to y equals f of x. But f of x is 3x to the third plus 2x minus 1. That's our limit of integration, dy dx. And so we say that a is equal to 1 to 3. Now we have y evaluated between 3x third plus 2x squared minus 1 and 0 dx. And when we evaluate that, we just have this curve, 3x to the third plus 2x minus 1 dx. And then we have exactly what we had before, 3/4 x to the fourth plus 2/3 x to the third minus x, evaluated. I hate those little smudges that my hand puts on there. Evaluated between 3 and 1. And we get the same answer as our previous way of doing it. Now this is the superior method. They don't usually teach this until second course in calculus, but I honestly think that this is the better way to think. I mentioned that before, but it all comes down to thinking about the problem and how it's set up. And so you can do this for any function. Let's take a look at another one. Let's delete that. We don't need that anymore. Let's delete this. We don't need this anymore. And let's we'll just keep that. I think that's beneficial to keep. So let's look at another function. Let's look at the cosine function. Where we have theta and y And this is 1 and minus 1. And we have pi, and we have let's make it as easy as possible. That's 2 pi, that's pi. So we're 0, let's see, cosine, we're 1 at 0, this is 0. At pi on 2, the function is 0. At pi on 4, it's at square root of 2 on 2. So we're going to oops, our pen isn't working. And then this is minus 1 over here. And at here, we're back to 0. And we're back at 1 here. It's not the prettiest cosine in the world, but now let's say, now this here is, that's, what is this, 3 pi on 2? Let's see, this is pi on 2, this is 3 pi on 2. And this is 1 pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, 5 pi on 4. And let's say this is 6, 7 pi on 4 and 2 pi. Let's say we want this area here under the cosine. We want what this area is. So we say that dA equals dy dx, and our area then is between 7 pi on 4 to 2 pi, and our limit is between 0 and cosine of theta, dy dx, so dy d theta. And then we end up with an area equals, and actually this should be, well, we'll leave it at that. 7 pi on 4 to 2 pi cosine theta d theta. And then we have area equals minus sine of theta between 2 pi and 7 pi on 4. And this is equal to, area equals 2 minus sine of 2 pi minus negative sine of 7 pi on 4, and that equals, and sine of 2 pi is 0, so we have sine, the negative signs cancel, sine of 7 pi on 4, which is equal to square root of 2 on 2, which is approximately 0.707. And that's going to be the area under the curve at that point. So in this segment here, I have a methodically derived proof or demonstration of the equivalency between the Riemann sum and integration. And this connection to integration is also a connection, mathematical connection to derivatives, because really integration and derivatives are the flip side of the same coin. So basically, this Riemann sum is a phenomenal thing because it equates well-established Euclidean geometry and principles of mathematics that are well recognized and accepted to the concepts that underlie calculus, especially the concept of a differential or infinitesimal. In particular, the differential areas being dy dx, they're infinitely small, and the sum between the bounded limits is exactly the area. And that's what the Riemann sum, when you derive it, shows that the Riemann sum using Euclidean ideas provides a means to the exact area under the curve. So it's a pretty remarkable thing. Well, I hope that helped in your understanding a little bit of the fundamental theorem of calculus, or what they call the first fundamental theorem of calculus. But this is the crucial one. This is the one that they teach you in calculus courses because it forms the basis of making that connection between Euclidean geometry and integration and differentiation. So again, I hope this has been helpful, and we'll move on with more examples, many more examples of integration, methods of integration, and many other topics that depend on integration. So wish you the best and stay safe with the COVID